Have you ever stopped to think about what happens when automated machinery flawlessly executes a super complex movement? Well, there's actually a hidden hero operating totally behind the scenes. These massive, powerful systems, they don't just move. They move safely and with absolutely pinpoint precision. So today, in this explainer, we're unpacking the invisible technology that quietly runs our modern world: industrial encoders.
Here's a quick look at our roadmap for today. We'll be covering what is an encoder, incremental versus absolute encoders, solid versus hollow shafts, common encoder failures, and finally, choosing the right encoder. Okay, let's dive right into this.
Section 1. What exactly is an encoded?
Picture this. You've got a massive robotic arm assembling a car, or maybe an enormous offshore crane maneuvering tons of heavy cargo over completely turbulent ocean waters. Now, the sheer power of these machines is obvious, right? But how exactly do they move with such exact millimeter precision without just crashing right into their surroundings? The chaotic environment of heavy industry literally leaves zero room for error. The control systems need to know exactly what the mechanical parts are doing at any given millisecond.
So, to answer that, at its core, an encoder is basically an electromechanical sensing device. Think of it kind of like a translator. It sits right on a moving part, converts mechanical motion into electrical signals, and then feeds that real-time digital feedback, stuff like position, speed, and direction, straight into a controller, like a programmable logic controller or a PLC. The PLC then uses all that data to make these incredible split-second adjustments.
Let's take the optical encoder, for example, to see how this actually works. Inside, an LED shines a beam of light through a rotating code disk. It's actually a lot like the spokes on a bike wheel, patterned with these opaque lines. As the shaft turns, those lines interrupt the light. Then a photodetector assembly catches that flicker, instantly translating that light-on, light-off action into a digital pulse signal. It's just ones and zeros that the controller can read in an absolute flash.
Moving on to Section 2, incremental versus absolute encoders.
So the crucial point is understanding the difference between measuring a relative change versus knowing an exact position, especially when things suddenly go dark. Incremental encoders, they measure relative change. They know the shaft is moving and how fast, but if the factory loses power, they suffer from total amnesia. When power comes back, they actually have to physically move to find a starting index before they can give you useful data. Absolute encoders, on the other hand, measure the actual true position, using a unique digital code for every single point of rotation. If power goes out, they have perfect memory. The instant power returns, the absolute encoder knows exactly where it is without having to move a single inch.
When we look at the specs, the architectural differences are pretty massive. Incremental encoders give you simple pulse trains, up to 10,000 or more pulses per revolution. Not bad, right? But absolute encoders, they output a highly complex, unique multi-bit digital code that represents millions of unique positions. And because absolute encoders are processing way denser data, they require more complex serial communication and, naturally, a higher upfront investment. But we really have to look past that initial price tag. While the upfront cost definitely favors the simpler incremental encoders, you've got to factor in the real-world operational costs. If your system requires an operator to manually re-index the machinery every single time the system powers down, well, those minutes of lost production downtime quickly add up. Over the lifespan of a heavily utilized factory line, that supposedly cheaper incremental option might actually end up being significantly more expensive just because of all that lost time.
All right, Section 3, solid versus hollow shafts. Now, what's really interesting here is how we handle major spatial constraints mechanically. A traditional solid shaft encoder requires an external flange and a flexible coupling that adds bulk and makes it highly prone to mechanical misalignment from motor vibration. But the hollow shaft design, it's incredibly elegant. It essentially eliminates its own shaft entirely, slips directly over the motor shaft, and locks on with a clamp and tether. It keeps things super compact, absorbs shocks beautifully, and practically wipes out the misalignment issue.
Let's look at Section 4, common encoder failures.
Consider the intense, really gritty man versus nature conditions of a steel mill. You've got extreme heat, grease, and microscopic metallic dust just flying through the air. If that dust gets inside the encoder, it causes disk contamination, instantly corrupting those super delicate optical signals. Or think of an offshore oil rig. The constant, punishing ocean waves cause continuous machine vibration and environmental shock. This leads to shaft misalignment and totally destroys the internal bearings. And then add in the unseen threat of electromagnetic interference when unshielded cables are run next to high-voltage lines. You've got a perfect recipe for total system failure.
But don't worry, we can definitely engineer around these hazards by following a few solid best practices. First, always match your housing to the environment. Choose ruggedized, sealed housings for specific marine or heavy-duty environments. Second, protect those internal bearings by using flexible couplings to guarantee proper motor shaft alignment. Third, practice strict electrical discipline. Run your industrial-grade shielded cables completely separate from high-voltage lines. And finally, always ensure proper grounding and use surge protectors to block those sudden voltage spikes.
Bringing it all together in Section 5, choosing the right encoder. Let's move to our next point and see how this builds a framework for your actual application. Monitoring a basic conveyor belt speed, a simple, cost-effective incremental encoder is completely fine. But if you're running a rotary indexing table or needing servo motor feedback where exact position must be known immediately on power up, you absolutely need an absolute encoder, ideally with serial communication for that high resolution. And for extreme conditions, like steel plant loopers, only a heavy-duty absolute encoder is going to survive that heat and vibration.
Let's just take a quick moment to appreciate the sheer capability of modern absolute encoders. They can reach up to 25-bit resolution. What does that actually mean? To put that into perspective, it means a single encoder can break down one 360-degree rotation into over 33.5 million distinct positions. That is a staggering, invisible level of extreme precision. It's exactly what's required for complex 5-axis CNC machines and advanced robotics to operate flawlessly without a single hitch.
We're constantly demanding our automation systems to perform faster and more intricately than ever before. As the demand for complex, multi-axis robotic automation surges across global industries, these hidden devices of precision are going to become the absolute bottleneck of our progress. So the real question is, how much further will we push the physical and digital limits of these hidden devices of precision? I really hope this explainer has given you a newfound appreciation for the incredible tech making it all possible.
If you found this explainer helpful in grasping the complex and fascinating engineering, like, share, and subscribe to @Makers Junction on YouTube for more highly professional, basic to advanced engineering content. Keep exploring, keep building, and we'll see you in the next explainer.